Hi friends, welcome to follow up. Let's have a look at problem 239, sliding window maximum. This is today's daily challenge problem, and this problem is marked as hard by leetcode. Actually, its logic is rather straightforward, and in this video, we're going to explain a solution based on monotonic stack. So here we are given an array of integers called nums. There is a sliding window of size k, which is moving from very left of the array to the very right. So we can only see the key numbers in the window. So each time the sliding window moves right by one position, we would like to return the maximal sliding window. So here the problem asks us to return the maximum in each of the window. For example, here the maximum is 3, so we return 3. And then here in this one, so in this 3, -1, -3, the maximum is again 3, so we return we corresponding to 3. And for example, if you look at this one, the maximum is 5, so we're going to have 5. So similarly, you get 7 for the last size key window. So in the second example, the length of this num list is equal to the window size key. So the output is 1 in this example. The constraints are the following. First, the length of the list is bounded below by 1. In other words, it's not empty, and which bounded above by 10 to the power 5. So it can be very long, it means. So the numbers or the elements in the list, it can be negative, can be 0, can be positive, but in absolute value, they are bounded by 10 to the power 4. And the last item in the constraints is an consistency one, which basically says that the window size is no larger than the nums list length. So with that said, we are ready to do the coding. And in between, we are going to explain the logic. So here we are going to present two formats of the same solution. So for the first one, we aim to understand the logic, and for the second one, we do some slight optimization to make the code more compact. So now let's first I'm going to initialize a result variable. So this is the empty list. We're going to return the number of the elements corresponding to the maximum in each of the window. So here, for example, if nums have length n, so this result will have length n minus k plus 1, right? So this is the one thing. So next, we want to use the standard monotonic stack trick. So let's initialize a stack. So here I'm going to use the collection deck. So you can actually just use the vanilla list. That will be fine. So now let's first get the first window. So we are going to iterate for I in range k. So what we want to do, we not only store the maximum, we want to store we want to maintain a locally decreasing stack so that within this window, so the final state, it includes the maximum element in the to the left, and then it also prepares for the next sliding window, right? So here, what we want to do is it's very standard, well stack, and so this next logic condition is a standard monotonic stack condition. If nums stack -1, in other words, at the tail of this stack, if this number is less than or equal to nums I, so we're going to do pop operations, stack pop. So this one, especially the second one, is the monotonic stack condition. And this is basically the standard monotonic stack operation. So with that said, afterwards, so if we exit this while loop, there are two possibilities. Either stack is empty, or the element, the top element at the stack will be strictly larger than nums I, right? And then we're going to stack append this I. So notice that this monotonic stack stores indices. the indices corresponding to the values of the list, but in the local stack, it's going to be decreasing. In other words, the um, the element in the bottom of the stack is corresponding to the largest element in this window. So this will give us the first element in the result, right? So what we want to do, append, so stack 0 actually. So this is the one preparation step. So next we are going to do sliding windows. So for I in range k up to the length of this num. So we want to include a new index I, right? And then in the stack, there might be several elements, but if the bottom element is equal to I minus k, so we should pop that because the current window should have starting from I minus k minus 1 and ending at I, right? So the current window will be from I minus k minus 1 and ending at I. So if you do the counting, so starting from I minus k minus 1 up to I, both inclusive, this will be k elements, right? That's why I minus k, this index is not going to count in the current window. And then what we're going to do, if stack if stack is not empty and stack the bottom element equals I minus k. So this means this number cannot included in the current window. So we're going to do one time pop operation. This is the pop left. That's why we use deck here. We use this pop left operation. If you use the vanilla list, so here you're going to write stack pop at index 0, right? So then we are going to again do the same thing, right? Let's copy this part. Well, stack and the top index in the stack corresponds to a number smaller than the current number, no larger than this one. So we're going to do continuous pop operation. So afterwards, we do the stack. Then the current stack state will maintain a monotonic indices. Monotonic means the corresponding element in the stack is decreasing. So here, the bottom element will correspond to the largest element in the current window. That also explains why we do this one-time pop operation if it occurs, if the condition occurs, right? So in this case, we're going to do result append num stack 0, right? So here, sorry, so here we need to append still num. Now we are not appending indices, we are appending the corresponding elements. So after that, so we can return the result. So this forms one solution format. So before we move to the second solution format, let's do a test first. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases successfully. So now let's look at the strategy of optimization. So here we notice that we basically repeat this part, right? So here we have one check. So we want to compact all this thing into one part. Let me copy the function signature. We'll change this one to be version v1. So now what we want to do is that we want to squeeze the two parts above into one. So this is actually very straightforward. So stack equals empty. So then also we initialize a result variable as above. And then we're going to iterate, right? For I in range, we're going to write length num. So then we're going to see if I is greater than key or less than key, right? So basically, first we are going to directly using monotonic stack. Well, stack and stack the top element in the stack will this if this one is less than or equal to the num I. what we are going to do is to do pop operation. So stack pop. So again, after we exit this while loop, so two possibilities. Either stack is empty or the top element in the stack corresponds to a number strictly larger than the current number. And then we are going to do stack append I. So that also explains why locally the stack will store indices corresponding to decreasing elements in the nums. So here, then we want to check if we need to do append operation in the result. So here we want to check if I minus stack 0, if this is greater than or equal to k. If this is the case, so we're going to do pop operation, right? Because here what we want to consider actually is index. So this means that I minus k is greater than or equal to stack 0, right? But here we consider k element. The k element actually is starting from k I minus k plus 1 up to I, right? If you count this one, so this I minus this number and then plus 1. So starting from I minus k plus 1, ending at I. So these are k indices, right? So that's why we see if I minus k is greater than this one, it means we this index stack I. So it's actually less than or equal, less than is very small, right? So it's less than, strictly less than this number. And then we need to pop that because in the current window, this indices is not included. So then let's see if I is greater than or equal to k minus 1. So then we begin to append element in the result, right? So here result append. So the stack bottom element, and then so we're going to call this, right? None. This is the thing. So here we want to use pop 0, but let's do something like this. So collections deck. So then they would just need to pop left, right? So this way it might accelerate a little bit, but from the time complexity point of view, they're the same. And then we just need to return the result state. So this solution format actually is the same as the first one, but the first one is more detailed, which is going to help us digest the logic. The second one is more compact. So before we move forward, let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So that's basically about it for this specific problem. So actually in our channel, there's a playlist called monotonic stack. If you are interested in such kind of problems, you're welcome to check that playlist out. With that said, that's it. Thank you.